Okay, in this video we're going to look at total internal reflection and critical angles. So in order to understand total internal reflection, you need to realise that at any boundary, even when refraction is occurring, it's still possible to get some form of reflection. So for example, when we draw in our line of incidence, there's our normal. We would expect that we get, if we go from, say, air to glass as we did in the last video, then what we'd expect is it bending towards the normal. But not just that, we also get what we call a partially reflected ray, like that. So you get a little bit of reflection at that boundary. What total internal reflection is when all of the light is no longer refracted, it's reflected. And this only happens in very specific circumstances. So total internal reflection occurs at any angle beyond what we call the critical angle. So imagine this time we're going from glass to air. That orientation of materials is important, and we'll come to it very shortly. What we observe happening here in this situation is when the angle of incidence is equal to something called the critical angle C, or theta C in this case, then what we observe is a refraction of 90 degrees to the normal line. So if I draw in my normal line again, so that's my normal line in the air after the glass air boundary, what we'd expect is the refracted ray to be at 90 degrees to the normal line. That is when the incident ray is at the critical angle. So we're observing a refracted ray at 90 degrees to the normal line. So what happens then when we extend that line, we change that line very slightly to be a line that is greater than the critical angle. So we've got an angle here of theta that's greater than the critical angle. Well, what we observe then is this process called total internal reflection, or TIR for short. It's not just a partial reflection anymore. None of the light is refracted, it's all reflected because the incident ray is greater than the critical angle. So what we've got here is, as I suggested, this can only happen in a very specific circumstance, when it's going from glass to air. i.e., it's going to go from a high refractive index to a low refractive index. Total internal reflection can only happen when the beam is going from high to low. It can only happen because when you're going from high to low, you're bending away from the normal line. Going from low to high, you're bending towards the normal line, so there will never be a critical angle. So just bear that in mind as a factor that is required for total internal reflection to occur. But again, this is not just qualitative science that we need to be looking at here, we need to look at it quantitatively. So we can look at it from the point of view of, from the critical angle, we can use this to allow us to work out the refractive index of the material, i.e. the glass in this case. So we utilise Snell's law as we did before. N1 sine theta 1 is equal to N2 sine theta 2. And obviously N1 and N2 are the refractive indexes of the two materials before and after in each case. So this N1 is the refractive index of the glass. That's what we're looking to find out from this problem. Then what we can do is we can go, okay, well, what about theta 1? Well, theta 1, we can replace all of that with the letter C, because that is what's utilised for the critical angle in this case. Remember, the critical angle is the angle of which a light ray from the normal gives a refractive ray of 90 degrees from the normal. So N2 is going to be the air. Air is just 1, as you remember from the previous video. Sine of theta 2 is 90 degrees. Well, that's interesting because sine of 90 is just 1. So actually, 1 times 1, well, that's just 1, isn't it? So we can get rid of that. So we end up with an equation which is the n sine c is equal to 1. Now, bear in mind this only applies where the object goes from a unknown refractive index, i.e. n1 in this case, into air. It could go into something else, which means that this value would change right here to whatever it was going into. Not that you very often get asked that, but more often than not, it goes into air, and air has a refractive, so it's often air for N2 for critical angle calculations. And you'll see that is because it's in your data sheet written as I'm about to write it here. So we can rearrange this equation then to suggest that N1 is going to be equal to the 1 over the sine C, the critical angle at which we get a refractive ray of 90 degrees. And that is, again, very, very useful because if we're able to find n out, as we suggested in the previous video, n is equal to c over v, v being the speed of light in that medium. So effectively, the last two videos, we've just quite simply shown you the equations where we can utilise them to find out what the refractive indexes are of the material which light is passing through. And the end goal of this really is to utilise that refractive index to find out just what the speed of light moving through that object is, as more often than not a goal. Obviously, we can rearrange these equations to find out what the critical angle could be. We could look at refracted angles, incident angles to work them out, rearranging the equations however necessary. And that is what we're going to do in the next video.